Okay, so in this video, we're going to start talking about Newton's second law, which is probably one of the most important laws in physics, definitely one of the most important laws in this unit, because this is where most of the calculations for this unit are going to take place, is with Newton's second law. Okay, before we do that, I want to take a look at a do now question. And so this do now question says a free body diagram is shown for a box. Which of the following best describes the motion of the box? Okay, and so you can see the free body diagram here, and you can see the different answer choices available. So pause it here and try to answer this do now question on your own. Okay, so just by looking at this free body diagram, looking at the lengths of the arrows, we can see that the normal force going up and the weight, the force of gravity, I normally call this force of gravity, but they use W for weight in this case. These two forces, when you add those up, are going to cancel out. Likewise, if you look at the applied force and the force of friction, those arrows are also the same length, and so when we add those two forces are also going to cancel out. In other words, this FBD is showing a net force of 0, and because of Newton's first law, what that means is if the net force on an object is equal to 0, that means there's two possibilities. Either the object is at rest and remaining at rest, or the object is in motion and remaining in motion at constant velocity. Okay, and so if you look at the answer choices, B is a possibility, and D is also a possibility, and so the correct answer is actually F. Okay, so again, that just goes back to Newton's first law. An object at rest remains at rest, or an object in motion remains in motion at constant velocity unless acted upon by a net force. And the object shown here is not acted upon by a net force, therefore it has to be one of those two possibilities. Okay, so pause there if you need to look at that some more. All right, so let's go ahead and get into this unit. I do want to just kind of remind you that you can always view the feedback I give you on Edpuzzle videos by clicking back on the assignment once I grade it and scrolling down and clicking to see the feedback I give you. I do also want to remind you that Quest homework, it says question homework, but it should be Quest homework number 4 is going to be due probably late next week, and so please make sure that you're keeping up with those assignments. Please make sure that you're also keeping up with your OpenStax textbook readings as well. Okay, so let's go ahead and get into Newton's second law. So Newton's second law is the only quantitative law in this unit. This is the only law involving calculations. Okay, and it looks very simple, but is actually way more complicated than it looks. But here's what Newton's second law says. It says the net force acting on an object is equal to the object's mass times its acceleration. In other words, F net equals mass times acceleration. And usually I call this equation the killer bunny equation because it looks very cute and small and simple, but it's actually much more complicated than it looks. And it's actually a very powerful law. It becomes more powerful when you can apply calculus using it. But it's a very powerful law because on the left side we basically have information about all of the forces on an object, right? The net force is the sum of the forces on an object. We talked about that in the last video. And on the right side we have acceleration, which has to do with kinematics and it has to do with types of motion. And we've been doing problems with acceleration for the past couple of units. Okay, and so this equation is the equation that connects those two concepts, right? And so let's get into Newton's second law. And again, it looks simple, but it's actually very complicated. The thing that makes it complicated is net force and acceleration are both vectors. Okay, and remember when we say F net, we mean the sum of the forces on an object. But what we're adding is we're adding forces, okay, which are vectors. And when you add vectors, we talked about adding vectors in the projectile motion unit. Adding vectors can become complicated because then you have to worry about different components and adding the components together correctly. Okay, so we will get to that down the line. Okay, so we are going to start off with some simple examples. Before we get into that, these are just some general guidelines that I would recommend that you follow when you're solving problems with Newton's second law. I would always recommend you draw a free body diagram first. I would recommend that you determine whether or not the object is accelerating based off of the context clues given. Okay, if the object is accelerating, then the acceleration is not zero. If the object is not accelerating, like if you see something like the object is at rest or the object is moving with a constant velocity, then the acceleration is going to be zero, meaning that the net force is going to be equal to zero. And finally, one of the most important steps that a lot of people always do incorrectly is to write down the sum of the forces before you plug in any numbers. Okay, and as we go through examples, you'll see what I mean by this. Okay, but doing this before you worry about answering the question can help you answer the question easier. Okay, so let's do some simple examples. Okay, so example one. Go back for a second in case you need to add that to your notes. Okay, so example one, it says a ball is taken to space, ignore gravity, and is pushed by two different forces. One force has a magnitude of 10 newtons and is directed to the left. The second force has a magnitude of 15 newtons and is directed to the right. Assuming the ball has a mass of 2.5 kilograms, calculate the acceleration of the ball. Okay, so first I want to start with a free body diagram. And because we're in space, we don't have gravity. We just have these two forces. And I'm going to call this force, I'm going to call F1 and the other force I'm going to call F2, just to give them like a nice easy label. Okay, so the force to the left is going to be F1, and the force to the right is going to be F2, and that one is slightly longer because the magnitude is bigger. Okay, so I write down Newton's second law, F net equals ma, and because F net and a are vectors, you can basically think of this equation as two separate equations. Okay, you can think of it F net x equals max and F net y equals may. In this case, we don't have any forces in the y direction. Okay, we only have forces in the x direction. And so the first thing we want to do is, after the free body diagram, is determine is the object accelerating, yes or no? Well, we can look at the FBD and know that it is going to accelerate. And so I'm going to leave the acceleration in the equation. And then on the left side of the equation, I'm going to write down the sum of the forces. Okay, the sum of the forces looks like this. F1 plus F2 equals 2.5 times A. Okay, now you might wonder, like, why not just plug the numbers in right away? Because doing this step is going to come in handy later when we do more complicated problems. Okay, you might be able to look at that and be like, oh, isn't it just going to be like, 5? Yes, it is, but doing the step, writing down the sum of the forces before you plug in any values is, again, going to be important when we're doing harder problems. Okay, so F1, I'm going to put in negative 10 newtons because that is 10 newtons directed to the left in the negative x direction. F2, I'm going to put 15. And so the net force is actually 5 newtons. And by the way, I put F net x, I should also put AX here. Okay, so if I divide both sides by 2.5, then I get AX equals 5 divided by 2.5 is 2 meters per second squared. Okay, and that's the answer to the question. Very simple Newton's second law example. Notice that this object is accelerating in the x direction, but the acceleration in the y direction is 0 because there are no forces in the y direction. Okay, so we have a simple one-dimensional problem with Newton's second law. Pause there if you need to look at that some more. Okay, so let's take a look at example 2. Example 2 says, using Newton's second law, calculate the acceleration of the object shown to the right. Okay, so I want you to try to do example 1.5 on your own, and I want you to try to find both the x acceleration and the y acceleration. Okay, so pause it here and try to do example 1.5 on your own. Okay, so I'm going to write out my second law equation, F net equals ma. Okay, but remember, it's really two different equations because net force and acceleration are vectors. And so really I have an F net x equation and an F net y equation. Okay, and I asked the question, in the x direction, is the net force 0 or not 0? And just looking at the magnitudes, I can see the net force is not 0. Now, the length of this arrow is actually incorrect because it looks like the lengths are drawn the same. They should not be. That's a mistake. But just looking at the numbers, I see that there is a net force. Okay, and so there is going to be acceleration in this situation. And I write down the sum of the forces. Now, they, for some reason, label all the forces with F, which is kind of annoying. So I'm just going to go with it for now. Normally, these would have like different labels. Um, and then for F net Y, the net force is going to be 0 in the Y direction because there's two Y forces, but they're going to cancel each other out, right? And so basically what I'm going to have is I'm going to have 45 plus negative 45 equals 0. And so nothing interesting is happening in the Y direction at all. In the X direction, I have negative 45 plus 15 equals 3ax. Okay, so that's going to be a net force of negative 30 in the X direction. And so ax is going to be negative 30 divided by 3, which is negative 10 meters per second squared. Okay, so based off of the forces acting on this object, the object is going to accelerate in the x direction, but not in the y direction. Okay, so if I wanted to write the acceleration as a vector, I could write negative 10 x hat plus 0 y hat. Okay, so pause there if you need to look at that some more. Okay, so let's step it up a notch. There's actually an equation that allows you to calculate the force of gravity. Most equations that we're going to talk about don't have an equation for them, but the force of gravity does. Okay, notice as you're writing this in your notes that this equation I'm about to write has a condition. And the condition is that this equation is only valid close to the surface of a planet. Okay, so here is the equation for force of gravity close to the surface of a planet. The force of gravity close to the surface of a planet is approximately equal to the mass of the object times g, where g is the acceleration due to gravity. Okay, and the direction of that force, which is a vector, is the same as the acceleration due to gravity direction, which is down. All right, so pause it there and make sure you add that to your notes. And what we see from this equation, and force of gravity, by the way, is the same thing as weight. So sometimes this is called weight. What we see is that an object's weight does depend on its mass, but it also depends on the acceleration due to gravity. And so if I go to the moon, my mass might be the same, but my force of gravity would be different because on the moon, the value for g is not negative 9.8 meters per second squared. It's actually more like negative 1.6 meters per second squared. Okay, and so this equation, you can see the relationship between mass and weight. Okay, so with that in mind, let's do a simple example. A box with a mass of 20 kilograms sits at rest on a table. Draw an FBD and calculate the magnitude of the normal force acting on the box. Okay, so the first step you're always going to do is draw a free body diagram. Don't even look at the question, just draw a free body diagram. We have a box at rest on a table. We have force of gravity going down. I know there's a surface because it's on a table. And I know it's at rest, meaning that the net force is equal to 0. And so my free body diagram is very simple. It looks just like this. Okay, so next I'm going to write out my second law equation, F net equals ma. And in this case, I don't have any x forces, but I do have y forces. So I'm going to write down F net y equals may. And then I ask myself, is the object accelerating? Yes or no? Well, it's at rest and it's remaining at rest, so no, it's not accelerating. The right side of this equation is therefore equal to 0. And then I write down the sum of the forces before I plug in any values. Okay, so this is my second law equation right here. Make sure that when you're doing problems and you are showing a sufficient amount of work, you have to show the step. You cannot jump just to plugging numbers in. Okay, you must show this step right here. Now the question asks us to find the normal force there is not an equation for normal force. There is no way to solve for normal force without using Newton's second law. Okay, it's not like the force of gravity where we can just use an equation to calculate it. There is no equation for normal force. Okay, so the only way to solve for it is to use the second law, write down the sum of the forces, and then see it there in the equation. In this case, I can see that if I knew what Fg was, then I could find Fn because those two have the same magnitude, but one of them is negative because they add to be 0. Luckily, I have an equation for the force of gravity. And so to find that, I'm going to take the mass, which is 20 kilograms, and then multiply by negative 9.8 meters per second squared, because that's the acceleration due to gravity on Earth. All right, so I'm going to get my calculator, and I'm going to multiply 20 times negative 9.8, and I get negative 196 newtons. And once I have Fg, now I can go back in and plug in and find the normal force is 196 newtons. Okay, so that is example 2. So a little bit of a more challenging second law problem, but still not anything too crazy. Pause it there if you need to look at that some more. Okay, so let's take a look at, actually, we're going to skip example 3 just in the interest of time, but I do want to take a look at elevator problems. Okay, so please make sure you add this information to your notes. Okay, so what it says in the notes is that a scale, like imagine like a bathroom scale that you use to weigh yourself, is designed to tell you your weight, right? That's what you use a scale for. However, if you think about what a scale does, a scale, the number on a scale is the number of newtons that the scale is pushing on your body, right? And so that is actually the normal force. It's not technically your weight, it's actually the normal force acting on you. Now, under normal circumstances, like if you're at rest, as we saw in the last example, when you're at rest, the normal force and the force of gravity are equal and opposite. However, if you are accelerating, let's say you're in an elevator, that's actually not the case because what can happen is if you're in an elevator and you're accelerating, the number on the scale can actually change based off of whether or not you are accelerating. Okay, and we can see that by applying Newton's second law to the situation. Okay, and I do believe you have a problem similar to this on your quest homework. All right, so let's take a look at a situation with a man in an elevator accelerating upwards. Okay, so example 1 says a man with a mass of 65 kilograms accelerates upward in an elevator at a rate of 2 meters per second squared. If the man had a scale attached to his feet inside the elevator, what number would it read? Okay, now I want you to pause it here. Try to do example 1 on your own. Okay, go through the process, follow the steps that we've been using to solve Newton's second law problems. Try to do example 1 on your own, and let's see how you do. Okay, so let's apply Newton's second law to analyze this situation. Now, we have two forces, the force of gravity and the normal force. And the normal force is greater in magnitude than the force of gravity. Now, how do I know that? Because the man is accelerating upwards. And if you're wondering, how do I know there's a normal force? Because the man is standing on a surface. Okay, so this arrow is slightly longer than this arrow, although it's not drawn very well. Now, I write down my second law equation. I'm not going to have an F net x equation in this situation because there are no x forces. But I write down Newton's second law, and then I ask myself, is the object accelerating? And the answer is yes. In fact, we're actually given the acceleration here in the problem. So the right side of the equation I can immediately plug in mass times acceleration. So that should be y, not x, F net y equals may. And then on the left side, I write down the sum of the forces, Fn plus Fg. Okay, and now I look at the question. The number on the scale is not the force of gravity, it's actually the normal force, right? Because that's telling you how hard the scale is pushing on you. So if I want to find the normal force, to solve this equation, I need to know what Fg is. And I can calculate that because I have an equation for that. Fg equals mg. So I take the mass, which is 65, g, negative 9.8 meters per second squared. 65 times negative 9.8 is negative 637 newtons. And then I have Fn plus negative 637 equals 2 times 65 is 130. And then I can find the normal force. Notice, by the way, this is why we write down the sum of the forces before we plug in any values, because otherwise you're asking yourself, like, what's the equation for normal force? How do I find that? Well, there's not an equation for normal force. The only way to solve for normal force is to write out the sum of the forces and then get Fn by itself. Okay. Also make sure you understand that normal force and net force are not the same thing. Okay, so in this case, the normal force is 637 plus 130, which is 767 newtons. And that is the answer to example 1. And so what this means, and you can go on YouTube and find videos to show this, but when you're in an elevator with a scale underneath your feet, when the elevator is accelerating up, you actually gain weight, so to speak, inside the elevator, right? If you look down, the scale actually reads a number bigger than your weight. And I would demonstrate for this for you, but I'm not at school and I don't have a scale. But you can easily find videos on YouTube that explain this phenomenon. Okay, so when the elevator is accelerating up, you temporarily gain weight. All right, pause there if you need to write that down. And when I say you gain weight, you don't literally gain weight. It's just the number on the scale gets bigger than it normally would be. Okay, and then finally, example 2. Example 2 says a young boy with a mass of 25 kilograms rides in an elevator traveling upward at a constant velocity of 15 meters per second. If the boy was staying on a scale during this elevator ride, calculate what value it would read. Okay, I want you to pause it here and try to answer example 2 on your own. Okay, so this is this is how you would do example 2. The free body diagram looks very similar to the free body diagram in the last problem. The difference is that he is moving at a constant velocity. And because of Newton's first law, the only way he can move at a constant velocity is if the net force on him is equal to 0. So when I write down my Newton's second law, F net equals ma, okay, and I'm only doing it in the y directions because there's only y forces, this is equal to 0. So when I write down Fn plus Fg, those two forces now have to balance each other out. And so I can find the force of gravity of the boy just by using this equation. 25 times negative 9.8. I get negative 240 newtons, negative 245 newtons. And so I get Fn plus negative 245 equals 0. And so the scale is going to read the normal force, which is 245 newtons. Okay, so hopefully that's what you got for this question. In other words, you did not actually have to use this value because the velocity does not matter in this calculation. There's nothing in this unit that really explicitly has to do with velocity. Okay, force does not have to do with velocity. The fact that it's constant velocity, doesn't matter what that velocity is, tells you that the net force is 0, regardless of what that force actually is. Okay, so pause there if you need to look at that some more. Okay, so the next thing that we're going to do, we're going to stop this video here, and I want you to work on some of the problems at the beginning of your worksheet that you got in class. But the next step is that we're going to move on to more complicated problems in 2 dimensions. Okay, and so the next video is going to talk about friction. And with friction, you have to take into account both the x direction and the y direction. Okay, and so when we say F net equals ma, remember, we're actually talking about 2 sets of equations. We're talking about the net force in the x direction is equal to the mass times the x acceleration. And the same thing is true in the y direction. Okay, and so Newton's second law is actually two different equations, one for the x direction and one for the y direction. And understand that concept is going to be important in the next couple of videos as we're applying friction and inclined planes and pulley problems and stuff like that. Okay, so make sure that you're caught up in your notes. I want you to try to do some of the problems on your quest homework or some of the problems on your practice worksheet um, before you move on to the next video about friction. Okay, please let me know if you have any questions, and I will see you guys in the next video.